Module 8, Lecture B, Raising and Handling. By the end of this lecture, you will be able to raise built-in exceptions with informative messages that aid debugging and user feedback, use raise from to chain exceptions and preserve original error context when wrapping lower-level failures, and format and log exceptions using built-ins like strar, repr, and print for clear diagnostics. Raising exceptions clearly. Raising exception instances. When your program encounters a situation it cannot handle safely, you raise an exception to clearly signal that something has gone wrong, and normal execution should stop. This prevents the program from continuing with invalid or confusing data, and instead hands control to an error handler. For example, if a function receives a negative quantity for an order, raising an exception is better than guessing what the caller meant. Using specific built-in exception types makes the problem clear to both the runtime and human readers, so they can respond appropriately. When you create an exception, you are not just choosing a type. You are also explaining clearly what went wrong and why. You usually raise a built-in exception class and include a specific message that describes the error. For example, if a data import fails because a file is in the wrong format, the message should indicate where the problem occurred and what was unexpected. In a web application, if a form contains an invalid email, the exception should state exactly what is wrong and which rule was violated. This level of detail helps both developers and users quickly understand and fix the issue. Thoughtfully raising exceptions improves communication within your code and makes it easier to maintain. By choosing appropriate built-in exception types and writing clear, specific messages, you create reliable patterns that other developers can understand and use. In areas like payment processing or scientific simulations, different exceptions can signal whether the problem is caused by user input, system failures, invalid parameters, or missing configurations. This turns errors from confusing surprises into clear signals that support robust error handling and faster diagnosis. Python code, raising exception instances. This material focuses on how and why to raise exceptions with clear, informative messages. It shows that when a program receives invalid input, it should deliberately signal an error instead of continuing as if nothing is wrong. By raising explicit exceptions, beginners can see exactly what failed and why, rather than dealing with silent, incorrect results. This approach makes programs easier to debug, more reliable, and safer to use. The code starts by importing several type definitions from the typing module so they can be used for type hinting throughout the script. Type hints specify what kinds of data functions and variables are expected to work with. This makes the code easier to read and understand, and helps keep data handling consistent and predictable. In this script, these imported types are applied to function parameters and variables to clearly indicate their intended types. This function figures out how many paint cans are needed for a room based on its length and width in feet. It first checks that both dimensions are positive, and if not, it stops with an error. It then multiplies the length by the width to get the room's area, and uses a fixed coverage of 350 square feet per can. The area is divided by this coverage, and because you cannot buy part of a can, the result is rounded up to the next whole number. The function finally returns this whole number as the required number of paint cans. We create a list called example inputs that holds several pairs of room dimensions in feet. Each pair represents a length and width, such as 12 by 10, 15 by -8, and 0 by 9. These pairs are used to test the paint can calculation function, showing how it behaves with both valid room sizes and invalid values like negative or 0 dimensions. We loop through each pair of room dimensions in the example list and announce the current room size in feet. For each room, we call the paint calculation function to determine how many cans are needed. If the calculation succeeds, we report the required number of paint cans. If it fails because the dimensions are invalid, we catch the resulting error and read out its message. This way, problems with the input are clearly reported instead of failing silently, which makes debugging easier. This script shows how to use exceptions when calculating how many paint cans are needed for a room. It first checks that the room dimensions are positive, and if they are not, it raises a value error with a clear message. For each example room size, valid dimensions are used to compute the room area and then divided by the coverage per can, rounding up so the room is fully painted. Invalid dimensions trigger the value error, which is caught and reported instead of allowing a silent mistake. This demonstrates how exceptions help enforce valid input and prevent unnoticed errors in calculations. Exception messages and data. When you raise an exception, the message you attach is critical for explaining what went wrong. A vague message forces people to dig through logs or code, while a clear one states what failed, why it failed, and what to do next. For example, saying that the check-in date must be before the check-out date is far more useful than simply saying the input is invalid. Well-written exception messages act as living documentation, revealing your code's assumptions and constraints at the moment they are violated. When writing exception messages, include specific data so the failure is clear and easy to diagnose. Instead of a vague message like unsupported file type, state which type was received and which types are allowed. In data processing, name the exact value, column, and row that caused a parsing error. In financial systems, include the attempted amount, the limit, and the account identifier. Providing concrete values and identifiers gives enough context to quickly understand and investigate problems in complex systems. When writing exception messages, you must balance useful detail with security and privacy. Do not expose sensitive data, such as passwords or full credit card numbers. Instead, use safe identifiers like masked account numbers or transaction references that support staff can look up securely. For users, show a simple, non-technical message such as asking them to try again later, while recording more detailed, technical information in logs for developers. This approach keeps users safe while still providing enough information for effective debugging. Python code, exception messages, and data. When handling errors, use clear exception messages that include helpful context, so it is obvious what went wrong and where. contrast vague messages with detailed ones for the same validation failure to show how much easier detailed messages make debugging. At the same time, demonstrate safe logging practices that capture useful diagnostic data without exposing sensitive user information. The goal is to be specific and informative, while still protecting privacy and security. The code starts by importing the data class decorator, which helps create simple data-focused classes with less manual work. Using this decorator automatically adds common methods such as the initializer and a readable representation of the object. In this script, it prepares for defining a class that will store booking request information. This makes the class concise, efficient, and easier to manage. This code defines a booking request class using a data class, which automatically creates common methods like the initializer and a readable string representation. The class stores two pieces of information, the check-in date and the checkout date, both as text. This structure represents a booking request with specific dates and makes it easier to validate and process booking information in a consistent way. A validate booking function checks a booking request to ensure the check-in date is earlier than the checkout date. It compares the two dates, and if the check-in date is the same as or later than the checkout date, it treats this as invalid. In that case, it builds an error message that explains the check-in date must come before the checkout date and includes the dates that were provided. It then raises a value error with this message to stop processing and signal that the input is not valid. The process booking function takes a booking request and first tries to validate it using a separate validation function. If validation fails and raises a value error, the code moves into an error handling section. There it assigns a safe reference code, REF4829, and uses it to build a technical message that logs the failure details to the console. At the same time, it creates a user-friendly message explaining that the booking could not be completed and asking the user to contact support with the reference code. This approach logs the technical error while giving the user clear guidance without revealing sensitive information. In this example, we create a booking request where the check-in date is set after the checkout date to deliberately cause a validation error. When the booking is processed, the validation fails and raises a value error. The booking process catches this error, logs a technical message with a safe reference code, and avoids exposing sensitive details. It then prepares a clear, user-friendly message that tells the user to contact support and provide the reference code. This demonstrates how to handle exceptions while communicating appropriately with both technical staff and end users. This script shows how to handle booking errors with clear messages while protecting sensitive information. It defines a booking request with check-in and checkout dates and validates that the check-in date comes before the checkout date. If this rule is broken, it raises an error with a descriptive message. When processing the booking, the script catches the error, logs a technical message that includes a safe reference code, and gives the user a simple message asking them to contact support with that code. Running it with an invalid date order demonstrates both the internal log and the user-facing message, illustrating effective and secure error handling. re-raising exceptions safely. When handling errors, you may catch an exception to log it, clean up resources, or add context. Then let it continue upward. This is called re-raising an exception, and it is important because it preserves the original error details. For example, a data processing step that encounters malformed input should record the problem but re-raises the exception so a higher-level job manager can decide what to do. This approach lets each layer of the system do its part without hiding or losing critical error information. When re-raising exceptions, a common mistake is replacing the original error with a vague one, which hides useful debugging details. This can happen, for example, when a specific database error is caught, but only a generic message is raised instead. Developers still need the full error context to diagnose problems, even if users should not see sensitive details. A safer approach is to log the detailed exception internally while showing users a clear, simple message. This preserves technical information in the logs and still provides understandable feedback to the user. When re-raising exceptions, you should decide at which layer they are handled and turned into user feedback. Lower-level parts of the system, such as file or database access, should add helpful context to exceptions and pass them upward instead of hiding them. Higher-level layers, like user interfaces or APIs, then convert these technical details into clear, user-friendly messages. This way, developers keep detailed diagnostic information while users see concise, understandable feedback. Python code: re-raising exceptions safely. This lesson focuses on how to safely re-raise exceptions while adding helpful context. You will see how to log useful information about an error before sending the original exception up the call stack. The material compares poor re-raising practices, which can hide the original error details, with better approaches that preserve the original exception while still providing extra context. Simple functions are used to illustrate the difference between bad and good re-raising behavior. The script starts by importing Python's random module, which is normally used to generate random numbers. However, in this code, the module is never actually used. This suggests it may have been included for planned random operations that were later removed, or as a placeholder for future features. In its current form, the import is unnecessary, since no randomness is introduced in the program. This low-level division function takes two inputs, the miles traveled and the gallons of fuel used, and announces that it is about to divide miles by gallons. It then performs the division to compute the result. However, if the gallons value is 0, this calculation will cause a zero division error, which is the standard Python error for dividing by 0. This mid-level trip calculation function focuses on safely computing miles per gallon while handling division errors. It calls a lower-level division function, and if a division by 0 occurs, it catches that specific error and logs a message describing what went wrong. After logging, it rethrows the same error so it can be handled further up in the program without losing any original details. If no error occurs, it simply returns the computed miles per gallon, preserving both correct results and useful error context for debugging. The function called bad re-raising example takes a distance in miles and a fuel amount in gallons and tries to compute miles divided by gallons using a lower-level division function. when a division by zero happens, it catches the zero division error. However, instead of keeping the original error information, it raises a new runtime error with a vague message. This approach discards the specific context of the original exception, making it harder to understand what actually went wrong. The runDemo function illustrates one way to handle exceptions by safely re-raising them. It begins by announcing that it will run a safe re-raising example using a trip calculation with 120 miles and 0 gallons of fuel, which is expected to cause a division by zero error. When this error occurs, it is caught, and the function prints the type of exception and its message. This preserves the original error details and makes it easier for the caller to understand and diagnose what went wrong. The code uses a print statement that outputs a blank line to separate different sections of console output. This visual break makes the results easier to read and understand. In this case, it clearly distinguishes the output from the safe re-raising example and the bad re-raising example. As a result, anyone reviewing the output can more easily see which results belong to which demonstration. In this example, we deliberately run a case with 120 miles and 0 gallons to trigger a division by zero error. We call the division function expect it to fail and catch whatever exception occurs. Instead of preserving the original error, the code replaces it with a vague, generic message. This shows how bad re-raising practices can hide the real cause of the problem and lose important error context for the caller. The runDemo function shows two ways to handle exceptions when calculating miles per gallon with 0 gallons of fuel. In the first, safer approach, the mid-level trip calculation function catches the division by zero error, logs it, then raises it again so the original error type and message are preserved and can be reported clearly. In the second, bad approach, a similar division by zero triggers an error that is caught and replaced with a more generic runtime error, which loses the original context. By printing the type and message of each error, the demo highlights why it's better to re-raise the original exception instead of replacing it with a less informative one. This script shows two ways to re-raise exceptions in Python using a simple division example. In the first approach, a function catches a division by zero error, logs the details, and then re-raises the same exception so the caller still sees the original type and message. In the second approach, the function replaces the original error with a generic runtime error, which hides the specific cause of the failure. When you run the demo, the first method clearly reports the division error, while the second produces a vague message. This highlights why preserving the original exception context is important for effective debugging. Exception chaining. Basics. Automatic exception chaining. Automatic exception chaining in Python links a new exception to one that was already being handled instead of discarding the original error. This means the runtime keeps both the immediate problem and the earlier one that triggered it. As a result, you get a clearer story of what went wrong, which is especially helpful in complex systems like web services or data pipelines. It allows you to trace the sequence of failures and understand both the direct cause and the underlying issue. Exception chaining helps you see the real cause of an error when multiple failures happen in sequence. For example, a program might fail to read a configuration file, then fail again while trying a fallback or writing to a log. Without chaining, you would only see the later error and might wrongly assume it is the main problem. With chaining, the runtime links the original configuration error to the later one. So, when you inspect the final exception, you can see both the immediate failure and the underlying issue that triggered it. In layered software architectures, automatic exception chaining is important because it lets developers trace errors back through multiple system levels. For example, if a network timeout occurs in a payment service and a higher layer tries to create a user-friendly error message but fails, the runtime links this new failure to the original timeout. This automatic linking forms a chain of related errors. So when developers see a high-level problem, they can follow the chain down to the root cause. As a result, diagnosing complex issues becomes more straightforward and reliable. Python code: automatic exception chaining. This example focuses on automatic exception chaining during nested error handling. When one exception occurs while handling another, the second exception keeps a link to the original failure, preserving the full context. By printing the final traceback, you can see both the initial error and the subsequent one, connected in a chain. Observing this chained traceback helps you understand how Python tracks and reports multiple related failures. The code starts by importing the traceback module and giving it a shorter alias for convenience. This module is used to handle and display error tracebacks, which are important for debugging and understanding how exceptions move through a Python program. Using an alias makes the code cleaner and easier to read, especially when functions from this module are called many times. The readConfig_value function is intentionally written to raise a file-not-found error as soon as it is called, with a message saying that the main configuration file is missing from the current directory. Its purpose is not to actually read a file, but to create a controlled error situation. This allows you to see how exceptions are raised, how they can be handled in a larger error management system, and how the original error context is preserved when exceptions are chained together. The handle configuration and log function is designed to deal with configuration errors. It tries to read a configuration value using another function, and if this raises a file not found error, it catches that specific exception. When this happens, it prints a message saying it is handling the configuration problem and switching to a fallback logging system. It then raises a new runtime error to indicate that logging has also failed while handling the original configuration error. And this new error is automatically linked to the original one to preserve the full context. We start by running the function that sets up configuration and logging, which may raise an exception if something goes wrong. Any exception is caught by an outer handler and stored as the final error. After catching it, we print a message that the final exception traceback will be shown, including any automatically chained errors. We then use the traceback tools to print the full details of the final error, including its type, message, and traceback, so we can see the sequence of problems that led to the failure. This script illustrates Python's automatic exception chaining. It first triggers a file not found error while trying to read a configuration value, then catches it and raises a runtime error to represent a logging failure. Python automatically links these exceptions, so the second one keeps the context of the first. When the final exception is caught, the traceback output shows both errors, demonstrating how Python preserves nested exception context to make debugging more informative. Using raise from explicitly. Using the raise from syntax lets you explicitly link a higher-level exception to the lower-level error that caused it. Instead of relying on automatic behavior, you clearly state that a new, more meaningful error is being raised because of an original one. This is especially important in layered systems, such as web applications calling database drivers, where raw, low-level errors are confusing to end users. By raising a new exception from the original, you translate the problem into your domain's language, while still preserving the original cause for debugging. In short, raise from creates a clearer error story without losing important technical details. Using the raise from feature is a way to control how errors appear across different layers of a system. In an e-commerce example, you do not want low-level issues like socket timeouts to leak out. Instead, you raise a clear, domain-specific error, such as a payment failure. By chaining the new exception to the original one, you keep the detailed technical cause available for developers, while presenting a simpler, more meaningful message to the rest of the system. This lets you hide unnecessary implementation details while still preserving full context for debugging and deeper investigation. Using the raise from feature helps separate responsibilities between software layers. For example, in a data science pipeline, the data ingestion layer can catch a low-level parsing error from a corrupted file and raise a clearer exception that names the affected dataset or time window while still linking to the original error. This makes logs and debugging tools show both the high-level context and the technical details. Over time, it leads to error reports that are easier for both users and developers to understand, trace, reproduce, and discuss. Python code, using raise from explicitly. Demonstrate explicit exception chaining by using the raise from syntax to show how a low-level failure can be wrapped inside a higher-level, domain-specific exception. This approach lets you signal a more meaningful error to the caller while still preserving the original cause. When you print both exceptions, you can observe that the full error context is kept, making debugging and understanding the failure much easier. This line defines a custom exception class called Payment Gateway Error, which represents higher-level failures in a payment processing system. By using a specific exception for payment problems, the code can report clearer, more meaningful error messages instead of relying on generic errors. This makes it easier to distinguish payment-related issues from lower-level problems, improving both debugging and error handling. This low-level network call function takes a card number as a string and simulates a network operation that can fail by raising an error. It first checks that the card number contains only digits. If any non-digit characters are found, it raises a value error with an appropriate message. It then checks that the card number is exactly 16 digits long, and if not, it raises another value error, explaining that requirement. If both conditions are satisfied, the function returns the message OK to indicate success. The process payment function takes a card number and calls a lower-level network function with it. If this call succeeds, it prints a success message with the result. If the lower-level call raises a value error, the function catches it and treats it as the original error. It then creates a clearer message saying that payment processing failed because of invalid card details. Finally, it raises a custom payment gateway error using the raise from syntax, so the original error context is preserved while providing a more specific, domain-focused explanation. We deliberately try to process a payment using an obviously invalid card number in order to trigger the error handling logic. When the payment processing function runs with this bad data, it raises a payment gateway error, which is then caught in the exception block. We print a message confirming that this specific error was caught, along with its error message. Finally, we also print the type and message of the original lower-level error that caused the payment gateway error, accessed through the cause attribute of the higher-level exception. This script shows how to use explicit exception chaining in Python with the raise from syntax in a payment processing example. A low-level network call checks a credit card number and raises a value error if the number is invalid. The higher-level process payment function catches this error and raises a custom payment gateway error with a clearer domain-specific message, while still linking to the original exception. When you run the script with an obviously invalid card number, it triggers this exception chain. The output displays the custom error message followed by the original value error details, demonstrating how raise from preserves the original error information for easier debugging. Inspecting exception links. Once you start using exception chaining on purpose, it is important to learn how to inspect the links between exceptions to see what really went wrong. The current exception is often just the visible symptom, while the original error is hidden underneath. By following these links, especially in layered systems like web applications, you can trace a high-level failure back to its root cause, such as a database problem or a network timeout. This deeper insight supports more effective debugging and leads to robust fixes instead of quick, superficial patches. When you inspect exception links, you usually rely on two things: the structured traceback that appears when an error is not handled, and the attributes of the exception object inside an error handler. When exceptions are chained, the traceback first shows the original error, then notes that another exception occurred while handling it, and finally shows the new exception's traceback. This order reflects the program's logical flow, revealing how one failure led to another. In complex systems, reading the traceback from top to bottom helps you follow the path of the problem across different layers and understand where it began and how it developed. When handling exceptions, it is useful to inspect them programmatically so you can trace high-level errors back to their original causes. This makes logs more informative, helping engineers see whether a problem comes from user mistakes, configuration issues, or infrastructure failures. Monitoring systems can then use this detailed error information to trigger targeted alerts for issues like timeouts, permission problems, or data corruption. In this way, exception chaining becomes a powerful tool for diagnosing and managing errors in production systems. Python code, inspecting exception links. This section focuses on clearly demonstrating chained exceptions and how they are linked together. It explains how the cause and context attributes connect one exception to another in a chain. You should see how to print the full traceback and then walk through the chain of exceptions programmatically. The goal is to make it easy to inspect and understand the sequence of errors that led to a failure. The code imports the traceback module and assigns it a shorter alias to make it easier to use throughout the script. The traceback module is important because it handles and prints stack traces, which help with debugging and understanding how exceptions occur in Python programs. Using an alias keeps the code cleaner and more concise, especially when traceback functions are called many times. The low-level division function takes two inputs, a miles value and an hours value, and returns the result of miles divided by hours. It does not include any error handling, so if the hours value is 0, it will cause a zero division error. Because it performs only the raw division, this function is considered a low-level operation that other higher-level functions can call and then handle any errors that occur. The mid-level speed calculation function is designed to handle errors from a lower-level division operation. It calls another function that divides 60 by 0, which triggers a zero division error. This original error is caught and stored, and instead of letting it continue unchanged, the function raises a new value error that states the speed calculation failed because of a division problem. The new error is explicitly linked to the original one using the raise from syntax, creating an exception chain that can be examined later. The function starts by calling a mid-level speed calculation inside a try block so it can handle any errors that occur. If an exception is raised, it is caught and stored for later use. The code then announces that it will show the full traceback, including any chained exceptions. Finally, it uses the traceback module to print detailed information about the error sequence, which helps explain what went wrong and how the final exception was reached. To examine an exception chain, we start by noting that we are about to follow the causes of a caught error. We store the caught exception in a variable representing the current error, then enter a loop that runs while this current error exists. In each iteration, we report the type and message of the current error to understand what went wrong. We then update the current error to its cause, moving step by step through the linked exceptions until there are no more causes to follow. This example uses a function called showTraceback and links to demonstrate how Python connects related exceptions. Inside this function, it runs a mid-level speed calculation, and if an exception occurs, it is caught and stored. The function then prints the full traceback of that exception, including any chained errors, using the traceback printing utility. After that, it follows the cause attribute from one exception to the next, printing the type and message of each linked error until there are no more causes. This shows how a single failure can be traced back through a chain of underlying exceptions. This script shows how Python exceptions can be linked and inspected. It begins with a division by 0 that raises a zero division error, which is caught and re-raised as a value error with extra context using the raise from syntax, creating a chain of exceptions. When the mid-level function is called, it raises this chained exception, which is then caught in the main function. The script prints the traceback to display the sequence of errors, then walks through the exception chain using the cause attribute to reveal the type and message of each linked exception. This demonstrates how chained exceptions help trace an error's origin and how it propagates through the code. Displaying exceptions clearly. Readable exception messages. Readable exception messages turn raw errors into clear, useful information. The exception type tells you the general category of the problem, but the message should explain in plain language exactly what went wrong, why it happened, and what to do next. Instead of a vague error, a message like failed to load customer data because the file was not found directly points to the missing file. This kind of clarity makes troubleshooting easier for both developers and users. When software runs in many different environments, clear exception messages are essential because you cannot know who will see them or what they already understand. A web app might show users a simple notice about a payment problem, while developers see detailed logs with technical data. In scientific computing, a message that explains a matrix inversion failed because the matrix is singular helps researchers locate the issue. By tailoring the level of detail and language to each audience, exception messages become powerful tools for communicating what went wrong and how to address it. Exception messages should be clear and informative without exposing unnecessary details. They should briefly state what operation was attempted, which resource or parameter was involved, and, when it is safe, the actual value that caused the problem. This is more helpful than a vague message that only says something went wrong. At the same time, you must avoid revealing sensitive information such as passwords or personal data. Balancing clarity with privacy makes exceptions both useful for debugging and safe to display. Python code. Readable exception messages. Readable exception messages make debugging much clearer and faster. Instead of vague errors that only say something went wrong, descriptive messages explain what failed and often hint at why it happened. Comparing a generic error to a specific one for the same failure shows how much easier it is to locate and fix the problem. When you print exceptions using their string form, you present these clear, clarifying exceptions, descriptive messages, in a user-friendly way. That helps both developers and users understand the issue. This function simulates loading a configuration value from user input by checking whether the input is a valid integer. If the input is not made of digits, it raises a value error. Depending on a flag, the error message can be either vague or more descriptive. When the descriptive option is used, the message clearly states what the invalid input was and what kind of value was expected. This added detail makes it easier for users to understand the problem and improves debugging by giving more context about why the loading failed. This description explains a function that reads a maximum connection setting from a string and converts it to an integer. It first checks whether the input string contains only digits, meaning it represents a valid integer. If the input is not valid, it raises an error and the exact message depends on a flag. With descriptive messages enabled, it explains that the value is invalid for the maximum connection setting and that an integer was expected. Otherwise, it raises a more generic configuration error. If the input passes the check, The function converts the string to an integer and returns that value. The helper function runs the parser and then shows any error message that occurs. It takes the exception, converts it to a readable string, and presents that to the user. This makes the error message clear and easy to understand. As a result, it helps both with debugging the code and with communicating problems to users. The demo run function begins by printing a label that identifies the test scenario. It then tries to interpret the raw input by calling the parsing function for the maximum connections value, passing the input and a flag for descriptive messages. If this parsing succeeds, it prints the resulting integer. If a value error occurs, the function catches it and prints a clear, human-readable description of the problem using the error message. This design makes it easy to see both successful results and what went wrong when parsing fails. This example compares two runs of the same code using an incorrect input value, but with different error messages. In the first run, the error message is vague and does not clearly explain what went wrong, making debugging harder. In the second run, the error message is more specific and explains the problem and how to fix it. This contrast shows that clear, descriptive exception messages are important for making debugging easier and more efficient. In this example, a variable is given the text value 30 instead of a number to represent invalid input. This simulates a case where user input should be an integer, but is actually a non-numeric string. The goal is to trigger input validation failure, so the code can show how it produces different exception messages in response to this kind of error. In this example, we call a demonstration function with 3 arguments to see how a vague exception message looks. The first argument is a label describing the scenario. The second is a variable containing the invalid input value 30. And the third is a flag set to false to request a vague error message. Inside the demonstration function, it tries to parse the input using another function that processes the maximum number of connections. When parsing fails, it catches the resulting value error and prints the associated message. This lets us observe the kind of vague error message produced when an invalid input is processed. A print statement with no content is often used to insert a blank line in the console output. This creates visual separation between different sections of output. It is especially helpful when running multiple scenarios or tests in sequence. By adding blank lines, the results from different parts of the program do not run together, making the overall output easier to read and interpret. In this example, we run a demonstration labeled Descriptive Message Example to show how a detailed error message is handled. The demo passes an invalid configuration value, the word 30, while the descriptive error feature is turned on. Inside the demo, we print the label, then call the function that parses the maximum number of connections. Because the input is not a valid number, the parser raises a value error with a clear message explaining that an integer was expected. The demo catches this exception and prints its message, giving the user a clear and helpful explanation of what went wrong. This script shows how clear exception messages make debugging easier. It parses a configuration value for maximum connections from user input and raises a value error when the input is not a valid integer. Using the same invalid input, the first version reports only a vague configuration error, while the second explains that the input is invalid and that an integer was expected. This contrast illustrates how descriptive error messages better guide users to understand and fix problems. Debugging with REPR. When debugging a program, it is not enough to know that an exception occurred. You need to see the exact structure and type of the data involved. Looking at an object's internal representation instead of its user-friendly display reveals its true type and contents. This can show, for example, that something that appears to be a number is actually a string with hidden characters, which explains why a conversion failed. Having this detailed view of the data's real state helps you find the root cause of errors in data processing and reduces guesswork. When debugging complex data structures like configuration dictionaries or JSON objects, it is important to look at the full technical representation of exceptions. This detailed view shows the exact structure, including quotation marks and type information, which can reveal subtle problems. It can expose issues such as keys that differ only by capitalization or values that are empty lists instead of being truly absent. In contexts like payment processing, this representation quickly shows mistakes such as a currency code in lowercase instead of uppercase, or an amount stored as text instead of a number, which might be hidden in a more user-friendly display. When debugging exceptions, it is important to log the object representations rather than user-friendly strings, because they remain consistent across different systems and environments. This consistency helps teams collaborate and analyze production logs without losing critical details. Unlike formatted messages that may be altered by interfaces, representations preserve the exact exception data, which is vital for tracking down subtle issues related to things like time zones or encodings. By recording exceptions in this reliable form, you can turn vague error reports into precise diagnostics and more easily reconstruct the program's state at the moment it failed. Python code debugging with REPR. Explain how the string and representation views of values differ when debugging exceptions and why that difference matters. Show how using the more detailed representation form can reveal hidden whitespace and the exact types of values inside error messages. Use simple examples, such as a failing type conversion and a dictionary lookup that raises an error, to make these ideas clear and easy to see in practice. We create a string that holds the number 42 with extra spaces at the beginning and a new line at the end. When we print it in the usual way, it looks clean and hides those extra spaces and the new line. However, when we use the representation function, it shows the string exactly as it is stored, including all white space. This illustrates that the representation view is more informative for developers because it reveals the precise contents of the string. We try to convert the text stored in the distance variable into an integer using the standard integer conversion function. If this works, we print the resulting number as miles. If it fails, the conversion raises a value error, which we catch with an exception handling block. Inside that block, we first print a user-friendly version of the error message, then print a more detailed representation of the same error that is helpful for debugging. We create a dictionary that stores financial data with an amount of 19.99 and a currency of US dollars. We first print it in a normal, user-friendly way, then print it again in a more technical form that clearly shows its structure and the string values. Next, we try to access a value for a tax rate using the dictionary's GET method. Because this key does not exist, the method returns the special value none, which we then display in the technical form to make it clear that no value was found. This script shows the difference between the normal string view and the representation view in Python, which is especially helpful for debugging. It demonstrates how text that looks clean can actually contain hidden spaces or newline characters that only appear in the representation view. This explains why some operations, such as converting a string to an integer, can fail and raise a value error. And the script contrasts the user-friendly and developer-focused error messages. It also illustrates how dictionary views look different in these two formats, and how missing keys return a value of none, which is clearly visible in the representation view. Overall, the script highlights how representation views give developers more detailed insight into data and errors. Printing stack traces. When a program fails, the exception message alone rarely tells the whole story, so you need to examine the stack trace. The stack trace is a timeline of function calls that shows which functions were called, in what order, and on which lines leading up to the error. For example, in a web app crash during checkout, it might show calls from a controller to a payment service and then to a database query where the problem began. By studying this sequence, you can pinpoint the true origin of the failure, which is essential for effective debugging and maintaining complex systems. In layered software systems, stack traces are crucial because they show the full path from where an error is detected to where it actually occurs. For example, in a data pipeline, a validation error might appear only as a job failure in the orchestration layer, making it easy to blame the wrong part of the system. A stack trace exposes the sequence of function calls and pinpoints the exact line that triggered the problem. This helps you quickly identify the responsible module and clearly communicate what needs to be fixed with your team. Stack traces are crucial for long-term diagnostics and observability, especially when combined with logging. In production, you typically cannot watch errors as they happen, so you configure the application to log stack traces whenever exceptions occur. Later, when a user reports a problem such as a crash, you can review these logs to see both the error messages and where in the code they occurred. This helps you pinpoint whether failures happen during specific operations, like image processing or calls to external libraries. Over time, recognizing these patterns supports structural improvements and makes the software more reliable. Python code, printing stack traces. This section explains how Python uses stack traces to make debugging clearer. It focuses on showing a series of nested function calls that eventually raise an exception, and how Python displays the path of those calls. It also introduces the traceback module as a way to print a clean, readable stack trace. Together, these ideas show how stack traces help you understand where and why an error occurred in your code. We begin by importing the traceback module, which is used to handle and display stack traces. A stack trace is a detailed report of the sequence of function calls that were active when an error occurred. This information is very helpful for debugging because it shows where and why the program failed. By using traceback, our script can produce clearer, more informative error messages, making it easier to diagnose and fix problems in the code. This description explains a function that converts a length measured in inches into miles. It first checks whether the number of inches is negative, and if so, it stops and reports an error because negative lengths are not allowed. If the input is valid, it calculates the distance in miles by dividing the number of inches by 63,360, which is the number of inches in 1 mile. The result is the equivalent distance expressed in miles. This function computes the distance of a trip in miles using the speed and driving time. It first defines a constant that represents how many inches are in 1 mile. It then finds the total inches traveled by multiplying the speed in miles per hour by the number of hours driven and by this inches per mile constant. Finally, it converts that total from inches back into miles by calling a separate helper function that performs the conversion. The program starts by announcing that it is beginning the trip distance calculation. This message lets the user know that the process is starting and sets expectations for what will follow. It also provides context for any results or error messages that may appear during execution. In this way, the initial announcement helps the user understand the purpose of the upcoming output. In this example, we try to compute a trip distance in miles using a function that takes speed and hours driven, but we intentionally pass a negative speed to cause an error. Because a negative speed is invalid, the function raises an exception instead of returning a result. We then catch this exception to demonstrate error handling. First, we print a simple message saying that an error occurred. Then we show just the exception message to briefly describe the problem. Finally, we print the full stack trace using the traceback module, which reveals where the error started and the sequence of function calls that led to it, helping us debug the issue. This script shows how Python uses stack traces to help with debugging. It defines one function to convert inches to miles and another to compute a trip distance in miles. When the script tries to calculate a trip using a negative speed, it triggers a value error in the conversion function. The program catches this exception, prints an error message, and then displays the full stack trace using the traceback module. Seeing this stack trace helps pinpoint where the error occurred and makes it easier to understand and fix the problem. In this lecture, you learn to raise built-in exceptions with informative messages that aid debugging and user feedback, use raise from to chain exceptions, and preserve original error context when wrapping lower-level failures, and format and log exceptions using built-ins like str, repr, and print for clear diagnostics. In the next module, Module 9, we will go over I/O and environment.
Thank you for your attention. See you all in the next lecture.